So I'll move on. All right, so the main observations, I think we've done the lab last night. You guys have a pretty good idea what the test questions are. And notice that the spark happens at a given distance, right? It's not 10 inches, it's not 20 inches, it's about an inch, or it's slightly less than an inch. All right, why that distance? What determines at what distance the spark is going to happen? Now that question becomes important in terms of figuring out where the lightning is going to strike, high ground versus the low ground. All right, so we know that the high ground is more likely to be struck by lightning, but 100% of the time. All right, so what determines whether the high ground or the low ground is going to get struck?
High winds took down a power line, trapping.
And we got a leftover question from previous weeks, and we've been asking this question for about a month, almost. The question is, so we understand that she's safe on the inside, right? So there's an electrical power line on top of the car. The car is part of the circuit. She's inside, she's safe, we get it at this point, because the net charge is going to remain outside. So the question is, why is it that she can touch the outside of the car where the current is, and she's still safe? All right, so that's the portion that never made sense to anyone to that point. So this week's lecture was electric potential. The test is going to be on electric potential. Electric potential is related to potential energy somehow. All right, so when you have like charges like that, there's going to be an electrostatic repulsion. So in order to bring this positive charge near the other positive charge, you have to do a tremendous amount of work. So work is a process of transferring energy, so which means that the energy gets transferred to the charge that you're bringing closer or nearby. All right, so the amount of work done against a conservative force like gravity, in this case the electrostatic force, is the amount of energy that you transfer to the object that you're bringing nearby. All right, so this work is the amount of energy that gets transferred to the object, so which means that this charge is now energized. So it's got potential energy, right? So what happens to the potential energy? Well, electrostatic force is a conservative force, right? So the amount of work that you do against that electrostatic force is the amount of energy that you store in the charge, within the charge. Now the charge got potential energy, so when you let it go, what happens? Electrostatic force, a conservative force, is going to take over. As soon as it takes over, it takes that potential energy and gradually converts into kinetic energy. All right, so the potential energy is going to get converted into kinetic energy. That's an important concept. It doesn't matter which path you take in order to bring this positive charge near this positive charge region, because the electrostatic force is a conservative force. And then as soon as you bring it near a positive charge region, it's energized. It's got energy now. It's got potential energy. And when you let it go, that potential energy is going to get converted to kinetic energy. So the path of motion does not matter. It doesn't matter how you bring the charge from point A to point B. All right, so it only depends, the energy, potential energy, only depends on the position, initial and the final positions of motion. So that's our potential energy, right? So the potential energy is the amount of work done against the conservative force in moving something against the conservative force. All right, so if you get a negative charge, if you bring it near a negative charge region, you energize it. Now it's got high potential energy. So that's your potential energy. Now potential is different from potential energy. So potential energy is it's the amount of energy stored within a charge, and you store the energy by bringing the charge near. If it's a negative charge, if you're bringing it near a negative charge region, you're energizing. If it's a positive charge, if you bring a positive charge near a positive charge region, you energize it. In essence. So that's the amount of work done against the conservative force field. Potential in this setting in particular represents whether the region is positively charged or negatively charged. All right, so if it's negatively charged, it's low potential. If it's positively charged, it's high potential. All right, so this negative charge has high potential energy by virtue of the fact that it's placed right near or next to a negative charge region, because it takes a lot of work to overcome that electrostatic repulsion. But it's placed near a low potential, meaning that it's placed right next to a negatively charged region. So low potential is negatively charged region, high potential is positively charged. All right, so electric field is the conservative force field in this case. Within this region, it's going to be constant. The reason it's constant is because the charges are uniformly distributed. And then also there's an underlying assumption that you don't see here. The assumption is that these are infinite planes, which means that all the charges will be equally spaced. Only surviving electric field vector is going to be the one which is going to be perpendicular to it, perpendicular to the surface. And these electric field vectors will remain parallel to each other all the way out to infinity. All right, so we do have a constant electric field region here. So within this region, all right, so this setup is important. And here's the reason why this setup is important. This is not like a lightning phenomenon. There's a uniform charge distribution. We got two parallel plates. They're flat. They're infinitely big, infinitely large. All right. And the reason why this setup is important because it creates a constant electric field region. And when you place a charge within this region, charge is going to experience a constant force. Constant force is going to cause a uniform acceleration, constant acceleration. When the acceleration is constant, motion is predictable. All right. So this setup is meant to give you predictable motion. So the motion of the charges will be at uniform acceleration. So it's going to be constant. All right. So we get an electron here at low potential, and there's a huge voltage or potential difference between these two regions. It's got potential energy. All right, so if it's free to move, electrostatic force is going to convert this potential energy into your kinetic energy, right? All right, so and this makes motion predictable. So potential energy of the charge is going to turn into kinetic energy because the mechanical energy is constant, it's conserved because the electrostatic force is conserved. All right, so everything that I described so far mathematically can be described a number of ways. All right, so one way of describing it is you got voltage difference, and voltage difference implies two opposite charge regions which are somehow separated from each other. All right, so one region is going to be positive charge, the other region is going to be negative charge. Positive charge region is a higher potential, the negative charge region is a lower potential. That's what it means. This represents two opposite charge regions. All right, this is your test charge placed within that region. As soon as you place the test charge within that region, it's energized. All right, so you got this two opposite charge regions, and as soon as you place a net charge within, or test charge or net charge within, the net charge is going to have potential energy. That's what it means. All right, so this is what this formula represents. V represents we got two opposite charge regions, and they're somehow separated from each other. They're not touching each other. There's a clear separation between these regions. One of them is going to be at a higher voltage, positive charge region. The other one is going to be at a lower voltage, negative charge region. And then you place a test charge within, all right, inside of it. And now this charge is energized. Okay, so this is what that formula represents. The formula represents a little bit more than that. Okay, so whenever you're dealing with opposite charge regions, there's an electric field pointing from the positively charged region towards the negatively charged region, or from high potential region towards the low potential region. And obviously these regions are separated through a distance r. And as it so happens, the voltage difference or potential difference is more adequately represented by this formula. So when we talk about voltage difference, we're talking about an electric field pointing from a high voltage region towards a low voltage region, a region which is separated through a distance r, in essence. All right, so, and all of a sudden, when you combine the meaning of E and the meaning of the definition of energy and work theorem from physics 1, you end up getting a better insight into this formula. The better insight is, this electrostatic force field, it's a force field, all right? It induces a force on a charge if you place a charge with it. And if there's a force acting on a charge, the charge is going to accelerate, it's going to get displaced. All right, so inherently, this field stores energy with it. So the energy is stored inside the field. Okay, so this is the sort of stuff that happens. You can read a book, there are books probably talk about it. This is the sort of insight you get when you have a really clear understanding of the definitions. What does a force field do? It induces a force on a charge in this case. And then what happens? The charge accelerates, it gets displaced. So which means that this force field has the capacity to do work, which means that this force field has already energy stored within. All right, so if you're talking about voltage or potential difference, if you're talking about voltage or potential, inherently you're talking about the amount of energy stored within the field itself. That's what it means. All right, and for you to be able to get to that kind of understanding, though, you need to have definition after definition after definition, and you need to be able to just pull them all together and have a really good understanding of it. All right, so that this thing no longer looks like an abstract. Oh, so that's voltage. What does it mean? I don't know. It's a formula. Nope, that's not how it is. That's not how it is done in physics. All right, so you need to just understand what that formula represents. What this formula represents literally is the amount of energy stored within the electric. All right, so that's the amount of energy stored, which means that that's the amount of energy that could potentially can get converted into a force that could cause displacement, provided that you place a charge within that region. So which means that that energy can get transferred to the charge. All right, so that's the understanding happens if you're just utilizing all these concepts from physics 1 as well. All right, so that's one of the things. So that's the voltage represents voltage difference. It's going to be expressed in terms of volts. Okay, so what else do we have? So this yellow region is where the energy is stored. The energy is stored within the electric field. And as soon as you place a charge within, all right, now the charge is energized. Okay, so what does it mean? Which means that this electric field acting on the charge is going to induce a force on it. All right, so that electric field acting on the charge is going to induce a force on it right there. And because of the force, it's going to accelerate, so it gets displaced. So what that means is the electric field is going to transfer the energy to the charge. So which means that now the charge is energized, now it's got potential. So as soon as you place a charge within this region of potential, the charge has got potential energy. All right, and then what happens if the charge is free to move? Its potential energy will get converted into kinetic energy. All right, so that's the story. All right, so a couple of applications for the multiple choice section of the test. Just remember within this region, the mechanical energy is conserved. All right, because these are standard test questions, multiple choice test questions usually. So if it talks about a capacitor, a problem, or electron gun, or whatever, we're always talking about a region that contains two opposite charge regions. More like area that contains two opposite charge regions. And so free charges, if you place a charge within this region, it's going to have potential energy. If it's free to move, its potential energy is going to get converted into kinetic energy. All right, so problem number 2, you guys may have to practice that. All right, just get used to expressing potential in terms of potential energy and potential energy in terms of potential. All right, so when the charges are free to move, there's going to be a conservative force field acting on it. So the conservative force field is going to act to reduce its potential energy and act to increase its kinetic energy. So which means that it's going to convert its potential energy into kinetic energy. That's it. So its potential energy gets converted into kinetic energy. All right. So one of the things, this is like conservation of mechanical energy formula. All right. So know how to turn voltage or potential difference into potential energy over the part. All right. So if there's voltage or potential difference, okay, between two opposite charge regions, if you place a charge within, it's going to automatically become like that. So that transition is important. All right, so there's nothing much there. All right, so that's problem number 2, just practice that. All right, so potential represents the amount of energy stored within two opposite charge regions. All right, so you place a charge within, that's got potential energy. And so the potential is going to be due to positive or negative charges. All right, so positive charges will give you a high voltage potential. It looks like a hill. If it's a negative charge, it's going to look like a well, potential well, usually. All right. So this is an equipotential line that you're looking at, or a curve in this case. Okay, so every single point is going to be at the same potential. So which means that the amount of energy stored within the field at these points will be identical. All right, so if you place a second charge here, by virtue of placing the second charge on this potential line, you energize the second charge. So the second charge is going to have potential line. All right, so that's the meaning of that story. All right, so potential energy represents the amount of energy stored within the electric field between two opposite charge regions through a distance of r. That's that. All right, so if you know the voltage, if you know the separation distance, you can figure out the strength of the electric field. Okay, so within that region. From that, you can figure out the amount of force acting on the charges. You can figure out the acceleration. You can figure out the speed using kinematics equations. Or you can just use the conservation of mechanical energy. All right, so gravitational potential energy is the energy stored in an object by the amount of work that you do against gravity by lifting something up. Gravitational potential is just going to be related to altitude. That's the amount of energy stored within the field. It's going to be directly related to the altitude or height or elevation. All right, so it's going to tell you the amount of energy stored within the gravitational force field at that altitude, at that location. So that's what it means. Electric potential is the amount of energy stored within the electrostatic force field or the electric field. All right, so that's going to depend on the strength of the electric field and the separation distance. Potential energy represents the amount of energy stored within the charge. All right, so the difference between potential and potential energy is in the case of potential, the energy is stored within the field. If it's potential energy, the energy is stored within the charge itself. So energy is stored in the charge. Potential is related to the strength of the electric field. Directly, stronger the field is, more energy is stored within the field. So which means that in essence, if the charges are free to move, more, the charges are going to be moving faster at the end. So larger the potential energy is, the larger the kinetic energy is at the end. So for a given electric field strength, the larger the separation distance is, the larger the voltage difference is, which means that the faster the charges will move at the end. All right, so speaking of the lightning phenomena, high ground versus low ground. All right, so our approach to this problem was, let's figure out the potential difference. All right, so let's figure out the potential difference between the high ground and the cloud and the low ground and the cloud. All right, so high ground in the cloud is 1 million in this case. Low ground in the cloud is 10 million. All right, so assessment is that it's more than likely 100% of the time, if this solution is correct, it should strike high ground, strike the high ground. Okay, so what does that mean? So this sort of conclusion can be arrived at, provided that you have a good understanding of the concept of voltage potential. Okay, meaning that you're able to interpret it different ways. When we're talking about the voltage difference being 1 million between the high ground and the low ground, what that means is this is the amount of energy which is going to be required per charge for the charge to be able to jump that gap. All right, so this is the amount of energy required. If the charges have this amount of energy, they should be able to jump that gap at whatever the strength of the electric field reaches that 10,000 newtons per volt. All right, so now they will acquire this amount of voltage or this amount of energy per charge sooner than acquiring the amount of energy which is 10 times as large. All right, so the charge will acquire this amount of energy much sooner, this amount of energy which is required to jump a smaller gap much sooner than the amount of energy required to jump a much larger gap. All right, so all things being equal, we expect that the lightning is going to strike high ground, and it should strike high ground 100% of the time, according to this logic. All right, so the voltage difference in this case is going to require, the voltage difference represents the amount of energy required for the charges to jump that gap. So they will acquire this amount of energy much sooner than they acquire an amount of energy necessary for these charges to jump a much larger gap. All right, so the problem with this logic is, though it's accurate, it's not 100% accurate. Lightning does not strike high ground 100% of the time, maybe about 70% of the time. Maybe. I'm just making things up. All right, so it's less than 100% of the time. So all of a sudden the question becomes, what gives? What gives? And what is it that we're not understanding it? All right, so what gives is the fact that we make tons of assumptions in solving physics problems. Yeah, it's just, the science is kind of messy. Okay, we never have a 100% accurate understanding of reality. The lightning phenomena is really not that well understood. All right, so if we're getting this right 70% of the time, which means that 70% of the time our assumptions are accurate. Okay, 30% of the time they're not accurate because we don't really quite understand how things are happening. There's quite that we don't understand that we discussed. We don't understand what caused the further separation of the charges. We don't understand where these positive charges are coming from, these positive ions from the ground. And then the ground it becomes polarized, but the charge distribution under the cloud, on the ground, they're not uniform. You don't get these. These are not like parallel plate capacitors, which are infinitely large. The real life, it just does not give you those infinitely large parallel plates. So it depends on the charge concentration. It depends on the charge concentration. You may have very high negative charge density here. You may have extremely high positive charge density here. And all of a sudden, they're going to be attracted to each other. You don't have a lot of electrons here. You don't have a lot of positive ions here. So obviously, that's the only way it's going to come in. And also, when these step leaders come down, it's just they go this way and that way, this way and that way. And then sometimes they end up missing all these other structures as well. So it depends on where the charge concentrations are and what these things are attracted to. All right, and eventually it just hits the ground itself. All right, hold on. So it was to the density. Yeah, I mean, David, absolutely yes. So it's the number of factors. You're absolutely right. What's on the ground also matters. Yeah, like the soil here is not going to be the same as the soil there. The contaminations, whatever the makeup of the soil is. There are a bunch of contributing factors that we don't quite understand or not able to keep track of. All right, so it becomes a random phenomenon. And then the next question is, if that's the case, high ground versus the low ground, we explained that. Okay, so I answered both questions in a sense. Okay, so the number one, high ground should be struck more often, according to this, because the charges require less energy to jump the gap. It doesn't happen all the time because the charge distributions are not uniform on the ground as well as under the cloud. So that just explains those two observations. All right, so electric potential. This is the analogy that we will get to use in the future, week after next. Instead of this crazy, deep understanding required explanation for voltage and potential, we'll just talk about, when to talk about voltage or potential difference, gravitational analogy is it's height difference. objects will fall from high potential towards the low potential. They will fall from high voltage towards the low voltage, and we will have the same analogy for charges, especially for positive charges. So from now on, 2 chapters from now, or the chapter after the next one, the current is going to be the motion of positive charges, despite the fact that the electrons are the ones which are moving. We'll just make the assumption that from now on, positive charges are the ones which are moving. This classical physics doesn't need to be highly accurate, and the charges will always fall from high voltage towards the low voltage. They will always move from high voltage to low voltage. All right, so the analogy that we get to use is this is high voltage, this is low voltage, high potential, low potential. Charges will always move from a place of high voltage towards the low voltage, and we will always assume that the charges are positive. All right, so it's a traditional way of doing it. It's exactly the same as everything is going to fall from a higher altitude towards the lower altitude, from higher elevation towards the lower elevation. And so positive charges will do the same. And then this is going to give us current. All right. So what drives current 2 weeks from now, you will find out is the potential voltage difference is the same as height difference in terms of gravity. So we will latch onto that really simplistic idea, and it's going to serve us really, really well. All right. So every single point at the same height is going to have the same voltage potential from a gravitational perspective. So these are known as the equipotential surfaces, and these are your equipotential lines. And so we will use the same concept or analogy using charges. All right. So highest potential surfaces here. Okay. So when you start to move away from the charge, so the altitude is going to start to go down, and so potential starts to diminish. All right. So these are your equipotential surfaces. Equipotential. So every single point is going to be at the same voltage or potential. So every single point is going to have the same amount of electrostatic potential energy stored within the electric field. All right, so if we can't do it, I think this is going to be our first lab. I just want to make sure that everything in the lab is working properly. I'm still trying to organize things. All right, so you can measure voltage or potential using a voltmeter, and so that's one of the things that we'll get to do. This one region is positive charge, the other region is negative charge. Okay, so whenever you're measuring the voltage, every single point on this line is going to measure the same value. All right, so once again, on paper, you will pick points at the same voltage, and then you will connect the dots, and then you will draw the circles. That's what it is. And then you're not going to be able to measure the electric field, but you can draw out the electric field. So the electric field is a conservative force field, and it always points in the direction of the diminishing voltage or potential. All right, so it's always going to point in the direction of diminishing voltage or potential equipotentials that you're looking at. So when you draw this out, it's always going to be 90 degrees to these lines that you drew previously in terms of representing these equipotentials. All right, so there's an interpretation that comes out of this, which is this. So the electric field always points in the direction of the diminishing voltage. So notice that the voltage is changing. There's a negative sign. This negative gives you the direction of the electric field. So electric field always points radially in the direction of diminishing voltage or potential. All right, so which means that in this direction, the voltage is getting smaller. That kind of makes sense. Okay, so what that means is literally, that means that the electric field always points from a positive charge region towards the negative charge. Always points from high voltage or potential towards the low potential or voltage. Okay, so that's what it means. All right, so now we are expressing the ideas that we already knew in a lot more mathematical formula, using a lot more mathematical formulas. All right, so there's a derivation here. Okay, let me just pull this forward. The derivation itself, I try to stay away from derivations which are not very useful in terms of problem solving. Okay, so this derivation is like everything that I've been describing verbally. Is this derivation tries to do the same thing mathematically, except when physics is presented like that, people don't get it. Students don't get it. I didn't get it as a student. I always felt that it was a waste of time. But if you're a graduate student or whatever, you kind of get used to expressing ideas this way. Okay, so instead of just going blah, 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 and then you come up with these derivations. So the only thing which is of importance here is not the way I stepped through the derivation here. So the conservative force is going to act on it. I'm just going to go blah, blah, just briefly. It's act to reduce the potential energy of a charge. All right, so you can express it in terms of a derivative in this case. And the work means force constant displacement. All right. And then the force could be expressed in terms of the electrostatic force field, which is the electric field. And then you can express the potential energy in terms of potential. All right, so potential energy per charge becomes potential, and then this becomes a derivation of stuff that we come up. Okay, so literally, this is the stuff that I've been describing time and time and time again. When this is done mathematically like that, you kind of see the math, but you don't understand the story behind it. But now that we came up with this formula, the meaning of the formula is the electric field is going to point in the direction of diminishing voltage or potential. All right, but this got some really powerful applications. Okay, now that we came up with the formula. All right, so when you isolate the electric field here, so what that means is electric field is pointing in the direction of diminishing voltage or potential, and it's pointing. This electric field is the component of the electric field which is in the radial direction. So the electric field is literally pointing radially away from a positive charge, and in the direction that is pointing, the voltage is diminishing. All right, so we've been discussing this forever, but it's got some amazing mathematical applications. So that's what we're going to be focusing on for the math portion of the test. All right, number one, we need an expression for a potential for a point charge. Once again, this story is here's the touch charge, and here's the source charge. Bring the touch charge near. By bringing it near, you do work. It requires work to bring it nearby. So the work that you do is going to go into the potential energy of it. So what is the potential energy of that? All right, so bringing a positive charge near another positive charge is like climbing up a pole. All right, so once again, we're using a classical mechanics approach to visualization. All right, so these visualizations based upon test charge being positive. All right, test charge is being positive. Your source charge is positive. Test charge is positive. If your test charge is positive, it's bringing a positive test charge near another positive charge is like climbing up a mountain. So that's the visualization that we use. Once again, your test charge is positive. So bringing a positive test charge near negative test charge is nothing. They're naturally attracted to each other. So it's like rolling down a hill into some kind of a well that you're looking at. So that's known as, I was going to say a gravitational law, but it looks like a gravitational law. All right, so there's a derivation here. All right, so the details on that, the derivation is important enough. Okay, let's just want to pull this up. All right, so what's happening is here's the electrostatic force field, so you can bring this charge near in this direction. Okay, and then in doing so, so voltage is going to be changing in this direction. It's going to be diminishing in that direction. So this is the electric field due to a point charge. So you can do back substitution. Now, you guys, these are simple integrals. You should be able to do this sort of stuff. So that's going to give you an expression for a test charge. That's going to give you an expression for the voltage for a point charge. Okay. One thing which is important here when you finish up the calculus of this thing is, all right, so here's the initial location of the charge. All right, so, and here's the final location of the charge. If you're looking at the initial location of the voltage, you're looking at the final location of the voltage. You can take the final location, extend it all the way out to infinity. So relative to infinity, okay, so relative to infinity, the voltage or potential is defined. Voltage or potential of a point charge is defined. Okay, that's just too much detail, so let's just get out of it. The only thing you need to know is the voltage due to a point charge is going to depend on the magnitude of the charge itself and then radial distance to that point. Okay, so that represents the amount of energy stored in the electric field at this radial distance. All right, so the voltage is going to diminish inversely as the radial distance. So that's all right. So the application of it is this. All right, so I'm not going to take you through the same derivation. So this is something that you need to practice. That's going to be your test question. Also, I'm going to give you guys the upgrade test number 1 for math section of the test next week. So you will have your test number 3 and upgrade test number 1. I'm going to answer the same question on the upgrade test number 1, which is the speed of the electron. All right, so I want you guys to just do it the right way this time, because the problems that I'm giving you are the problems that we will need, the solutions we will need in the future. Right? So hydrogen atom is something that we will always focus on. Some of you guys will have to take modern physics, and unfortunately our school does not offer it, so you will have to take modern physics somewhere else. And then if you have a really good understanding of the hydrogen atom, you can follow through the modern physics, because it's just going to evolve into the modern atom at some point. Okay, so, and it's important that you have this stuff in your head, or not in a book, not in your notebook, not where to find it necessarily. Make sure that it's in your head. This is something that you can visualize, because this is the atom that we use in classical physics. I just want to make sure that you guys know what kind of transition happens within this atom. All right, so your upgrade test, once again, I'm going to give you exactly the same problem. It's going to be the hydrogen atom problem. Make sure you know how to find the speed. Make sure you set it up, be able to explain it, be able to draw it out. And then at the very last step, just plug the numbers in. All right, so just do it symbolically. Know how to do it symbolically. And it helps if you just mumble to yourself, just explain it to yourself, explain it to someone else. All right, just put words, sentences whenever you're explaining. Okay, so hydrogen atom is here to stay. It's this the simplest model of the atom. And this model serves us really well in electricity and magnetism. So we'll just keep using it, but make sure that you know how to express it mathematically. So just focus on this one. So figure out what the ionization energy of the hydrogen atom is, be able to explain it and describe it while you're solving it, and make sure you draw things out this time. Right? So that's what we will do. So that's the one that we will have to focus on. Another thing that I want you to be able to do. Okay, so let's talk about the isolated conductor. So why is it that you're able to touch the outside of the metal where the charges, not charges, and not get electrocuted or shocked, either one? The reason is because there's no potential difference between inside and outside. How do we know that? Well, we know from last week or the previous week, using the Gauss's law, that there's no electric field inside. All right, there's no electric field inside because there's no net charge inside. All right, so the voltage difference implies a potential difference. That implies that we have two opposite charge regions. We don't have a second region in this case. All right, one region is charged, that's the outside surface. There's no charge within, so which means that that's an equal potential surface. The region is equal potential. So there's no potential difference between inside and outside. Well, if there's no potential difference between inside and outside, there's no reason for the charges. Nothing is forcing the charges to go through your body. So you can touch the outside of a conductor while it's sitting inside, you're perfectly fine. No potential difference, no reason for the charges to move across your body, which means that there's no electrostatic force pointing these charges or forcing these charges to go through your body. All right, I think most of you guys have that. All right, so it's like a car. This is the surface, this is where the surface is. So all the way up to the surface, there's no potential difference, but as soon as you start to move away from the car, there's voltage is going to gradually start to decrease. So, which means that you have to keep your feet together. Right? If one foot is here, the other foot is there, you will get shocked. So that's what happens. So the electric field, there's no electric field within. Okay, so which means that nothing is going to force the charges to go through your body. All right, so the outside surface is charged. All right, so the electric field is going to be strongest into the surface as you start to move away from the surface of a car. Obviously, it's going to diminish gradually. Inversely is the square of the distance in this case. All right, the thing to focus on, this is for the extra credit. When I say extra credit, the reason why I make this extra credit is next level up, meaning that when you guys take the same course over again, which you will have to, it's called NM, electromagnetics or electrostatics. Okay, so depending upon if you're an electrical engineering major, you may end up taking a whole course on this one. And regardless, everybody has to take a course on that. What's going to happen is problems will start to look like this. Okay, you will get to use tons of calculus. Right? I know some of you guys are taking or have taken not the electrostatics, the statics. Some of you guys are probably taking dynamics. Okay, so you know what I mean. Okay, now the emphasis at that point is going to be how do you structure this mathematically? Okay, in physics, I'm focusing more on the concepts and a little bit of, hey, you know, at the same time, I'm trying to apply it within the proper mathematical settings. And mostly I'm using algebra and trig, and sometimes obviously calculus when it's appropriate. In the engineering courses, there's an assumption that the physics is already covered. Let's have a much more organized mathematical approach. So they will present things within the setting. So that's the sort of stuff I'm making extra credit because I want you to get enough of a practice so you can make the transition. Okay, so the practice is this. How do you, okay, so it's a circular line charge. And my question is, what is the strength of the electric field in this direction? All right, how do you figure that out? All right, so the way to do that is you need to figure out the voltage first. All right, and this requires practice. So just figure out the voltage. So I came up with a voltage expression. And once you figure out the voltage, the next step is you have to use this concept. Okay, the formula that I came up with before, which is this formula, okay, right here. And so from that, you can figure out the strength of the electric field along the x direction, if you know the voltage. You can figure out the strength of the electric field along the y direction, if you know if the voltage is given. You can figure out the strength of the electric field along the z direction. Okay, so all of a sudden, this formula, this concept, the fact that the voltage diminishes in the direction that the electric field is pointing becomes huge in terms of problem solving. Okay, so for example, this was the voltage that we came up with for a circular line charge. So the only thing we have to do now is just express it in terms of this formula. So take the voltage, differentiate it with respect to z, and put a negative sign up front. And then we'll check to see if we come up with the same formula that we did from chapter number 23. And then when you do your algebra, your calculus in this case, you will come up with the same answer. And so that's what it is. You end up coming up with the same answer. So it's a much more powerful mathematical technique. much more powerful mathematical technique than using Calc 3, the vector calculus, and it works out beautifully. So as your test, what I want you to do is I want you to apply that concept to, this is going to be your, literally, this is your extra credit test problem. All right, so what I want you to do is find the potential of voltage at this point, P, and using that equation, which is A sub Z equals negative of the change in voltage along the Z direction, and then come up with this equation. All right, so come up with this equation. You should come up with the exact same equation.